Without further ado, I will pass you off to our host for today, Lori Koch, Director of Education Outreach. And we are delighted that you are here and trust that you're going to find some value and information that you might not have known before.
Today's program is a CLT discussion panel, where we've been, where we are, and where we're going. I'm Lori Koch, the Director of Educational Outreach at the American Wood Council, and my co-presenters, my co-panelists today are Levi Huffman from D.R. Johnson Wood Innovations and Iain MacDonald, who's the TallWood Design Institute Director. We have our disclaimer that's required, but we won't spend too much time on that or our copyright. This program is copyrighted. We are offering both AIA and ICC credit for today's program. And I'm going to assume most of you saw the course description when you signed up, so we won't linger on that or our learning objectives too long. As Marcy mentioned, I am our engineering host. I'm Lori Koch, our Director of Educational Outreach here at AWC, and our co-panelists today are Levi and Iain. Thank you for both of you for joining us, and thank you to all of our attendees for taking the time to join us this morning. So I'm going to be kicking things off with where we've been, focusing primarily on some definitions, some code acceptance, and a little bit of history, as much as I can cram into 15 minutes or so. After I'm done, Levi and Iain will each speak for about 15 minutes, and then again, make sure you stay on for our extended Q&A, and make sure you submit your questions as we go along, because we will be taking extra time at the end for questions. So Cross Laminated Timber, I'm going to assume many of you are familiar with it. We have done a lot of education on it at AWC through our webinars and other programs. So if you're looking for more in-depth information, please check out awc.org/education for some more courses. But it is a panel product. So as you can see, we have an illustration here that shows that we take nominal 2x lumber, so that's 1.5 inches the actual thickness, and we laminate them so that the adjacent layers are perpendicular to each other. And that allows us to develop a panel product that can be used for walls, floors, roofs, pretty much any part of the building that you want. And you can see this illustration here that we have at the factory here. We can have the openings all pre-cut, and it really does lend itself to an expeditious type of construction. The history of CLT goes back into the mid-80s, actually. The first patent for CLT was registered in France in 1985. Throughout the early 90s and into the early part of this century, the CLT technology improved, and we have seen the use of the material throughout Europe increased significantly. In England, for example, there's over 500 CLT buildings. So the United States and Canada have recently moved to adopting CLT in the last handful of years, and part of that effort has been led by the American Wood Council and Canadian Wood Councils and our partner organizations as well. Some of the supporting test data that we have, you can see here, this is one of our first tests that we actually did on CLT. This was an ASTM E119 fire test that was done back, I believe, in 2012, perhaps 2013. I don't remember the exact year, but the year the test was done isn't really so important as the results of the test. So this was a 5-ply CLT panel that had a layer of 5/8 inch type X gypsum on each side. The wall was loaded to approximately 87,000 pounds, which was the maximum capacity of the machine they had at this particular test facility. So, about 87 kips, that's a pretty substantial load. And this particular wall, you can see the point of failure was noted at 3 hours and 6 minutes, as you can see on the clock here at the bottom of the screen. So this was a pretty impressive test, and we're pretty happy with the results. This led to some additional fire testing. This was a multi-story fire test that AWC oversaw along with U.S. Forest Products Laboratory staff, and again, with the help of our partner organizations. This was done at the ATF Fire Research Lab in Maryland. So you can see we built a 2-story full-scale structure inside of the lab here. And we subjected it to 5 different fire tests. The illustration on the right is what the structure looked like. The picture on the left is one of the CLT panels after it was exposed to a fire test that ran somewhere in the neighborhood of 3 to 4 hours probably. But you see we lost 1 layer of CLT due to char. But the remainder of this cross section is relatively intact, and that's something that the performance of CLT is such that we do lose strength and this is true for all wood products, due to cross-sectional char, but the material that remains uncharred retains a lot of good structural capacity. And these are just some illustrations from one of the tests that we performed where we were testing the story compartment. And you can see that we had flashover occur in both sides of the structure. So the kitchen side is kind of this left large opening. We have a small hallway here. This is the kitchen living area, and then a bedroom area is on the right of the floor plan. We experienced flashover, the decay, and then this is what it looked like after all the burnt contents were cleared away. The contents. We saw that we were left with some char, but the overall performance of those tests was such that we were really pleased with the results, and we'll talk about what those led to later. So historically, as of 2015, cross laminated timber has been in the IBC. It's defined in Chapter 23, or I'm sorry, it's defined here, and you can see we have a reference to the production standard in Chapter 23, and that production standard is ANSI APA PRG 320. So there have been a few updates of it. This is a picture of the 2012 edition on the cover, but there are more up-to-date versions of this standard. So that's the 2018, I believe, is the most up-to-date version. And that's what's referenced in our newer versions of the NDS. So historically, we said 2015 IBC recognized cross-laminated timber. That 2015 IBC referenced the 2015 NDS. In 2018, we updated some things, added some stuff, and you'll see the CLT chapter that's in the 2018 NDS did indeed grow from 2015. In terms of IBC recognition, the 2018 NDS is referenced in both the 2018 and 2021 IBCs. And as I mentioned, we have our own product chapter here for Chapter 10. And it looks like many of the other product chapters that you've used in the NDS before. There shouldn't be anything in here that's out of the ordinary or seems too crazy to you. In terms of the 2018 IBC now, so we talked about 2015 moving into the 2018, IBC Chapter 6 is where we define our types of construction. And wood construction is commonly associated with types 3, 4, and 5 of construction. And obviously we have our subtypes within those, 3A, 3B, and all that. But in types 1 and 2, there are specific applications that permit the use of wood, but we usually see that in things like finishes. It's not something that we would see in the structural frame for types 1 and 2. Those are required to be non-combustible. In 2018, there was a pretty substantial reorganization of the heavy timber or type 4 construction. So just if you're in there and you were familiar with the 2015 IBCs, a lot of the things that were in Chapter 6 before have found their way into Chapter 23. So if you're in the process of updating or transitioning from the 2015 to the 2018 IBC, and some of the things that you may have been used to seeing in Chapter 6 seemingly have disappeared, they're still there. They've just moved to Chapter 23, which is the wood chapter. Going further, this is the language in the 2018 IBC. There was a provided clarification for this. So it does state that the exterior wall assembly is not less than 6 inches thick. That's a total assembly. So the CLT component of that assembly is a minimum of 4 inches in thickness. And then we would have, either gypsum board or other sheathing on the outside of that would then comply with your total 6-inch thickness. So that was something that was a clarification that was provided. And now, kind of moving, I won't get too much into where we are because I don't want to step on Levi's toes too much, but I will talk about the 2021 IBC because this is the fruits of the efforts of a lot of testing, a lot of work by the TallWood Ad Hoc Committee, and a lot of work by a lot of individuals throughout the ICC organization, as well as many other organizations. So we have a definition in 2021 IBC that defines mass timber, and we have 3 new construction types that have been added. So type 4A, type 4B, and type 4C. And I know that many of you have been on our other webinars where we have talked about a lot of the specifics with these different types of mass timber construction, so I won't spend a ton of time talking about the individual differences between them. The primary thing to know is that type 4C, it allows us to have fully exposed mass timber. It's also the shortest. Type 4B lets us go a little bit taller, but there are limits on how much exposed mass timber can be present, as well as limits on how close those exposed mass timber areas can be to one another. Type 4A is the tallest, but it does not allow any exposed mass timber, and it has requirements on how much of the fire resistance rating for the building element comes from non-combustible protection. So, and then we've just got some summary slides here that show the maximum height in stories. So like I said, type 4C is going to be our shortest allowable height. That would be 9 stories or a maximum height of 85 feet. For type 4B, again, we can go a little bit taller. We can go up to 12 stories, maximum building height of 180 feet, partially exposed mass timber. And then type 4A, this is our tallest allowable structure with 18 stories allowed or a maximum building height of 270 feet. And this allows no exposed mass timber. That takes us up to where we are now. So I'm going to go ahead and give the controls here to Levi, and he's going to talk about some of the manufacturing and applications and kind of the current state of the practice.
Thank you for having me here. My name is Levi Huffman. I'm the Director of Technical Services at DR Johnson Wood Innovations, and I'm going to give a little bit of a discussion on where we are now. So in cross laminated timber panels. So thank you for joining in, and let's get started here. Here's a picture of a project on the northeast side of the Burnside Bridge called Block 76 or Side Yard. It's a 5-story post and beam structure with cross laminated timber panels for flooring and roof. Just a neat little project that I wanted to share. So what is cross laminated timber? I know Lori touched on it a little bit. It's a secondary wood product, several layers of lumber stacked crosswise. It's bonded together with a structural adhesive, and it's generally anywhere from 3, 5, 7, or 9 layers thick. And this is something that, as Lori mentioned, has been produced in Europe for many years and in North America for a little less, but we've been doing it for about 5 going on 6 years now. And I'm going to go through you'll see some pictures of some projects that we've done that are out there, either us or others. This is the Nature see again in Portland. That's a 7-ply panel with a pretty good cantilever that's overhanging. But you can see the beauty of the wood and the actual, you know, the cantilever that's there. It's really great. Well, we'll talk about how cross laminated timber is made, and I think it's really important to note that in order to have a successful project in mass timber, you really have to have good team collaboration. So you need to have a developer that wants to design with wood, an engineer, an architect that has experience or is willing to gain experience in wood, you know, a contractor that won't shy away from building with wood or mass timber specifically simply because maybe they haven't done it before, and knowing that they've got fabricators and manufacturers on board that are experienced and really can help guide this team to a successful project. So I think that that's one of the main things with any mass timber project to be successful. It really does take a lot of team collaboration, and that's what we do currently. In order for any project to get started, what we like to do is take 3D models of these wood products. And what we're doing is modeling in, you know, not only glulam beams and columns, but the cross-laminated timber panels. And this is the model of that Block 76 project that I showed at the very beginning. And I think it's really important to note that the purpose of all this 3D modeling is simply to, you know, build the project in real life or in computer space prior to building it in real life. So, and what this does is it allows for a lot of, you know, not only clash detection and whatnot, but just any discrepancies between architectural and structural plan sets, working through any details, and just making sure that the project is going to be successful. Further, here's a couple other photos of other models. This was of a big feature stair at a university. And we're modeling in all of the connection details as well to make sure that we are going to be able to fabricate everything correctly. One last model. This is of that Nature Conservancy. This is of the inside, kind of an opposite view of what we saw in the picture before. But again, it's just making sure that we're laying out all the panels correctly, any glulam beams or miscellaneous metals that go along with this. There's always going to be some miscellaneous metals, maybe some other hybrid or you know, steel or concrete, and it's important to include all of those elements into these models prior to fabrication. Once we have our fabrication, or we have our 3D models complete, we create shop drawings, and then that's where we are sending our shop drawings out to the design team, whether that's the architect and the engineer, and just making sure that we're, you know, incorporating their design correctly in our drawings and our models to make sure that we are going to be fabricating these projects correctly. This is of a shop drawing of a fairly complex CLT panel with post-tensioned openings through the middle of the wall in order to have, this is I think a 7-ply shear wall. So really a complex shop drawing really for a CLT panel. Most are a little bit more straightforward. So what does it take to actually manufacture? I know we've talked about collaboration, but once we've got collaboration complete, we've got the 3D models done, shop drawings complete, then that's where the actual CLT manufacturing comes in. Essentially what we do is we grab the primary lumber selection, we group it, we grade that lumber to specific grades, we cut it to length, we apply adhesive, we lay up the panel and press that panel. Once that panel's pressed, the adhesive is cured. We then go on to quality control, fabrication, sanding, sealing, etc. Here's a photo of panel layup and another photo of the adhesive being applied to the panel in between layers. The picture on the right is of a CLT billet, basically fresh out of the press. There's a little bit of trim that you can see there. The point of that trim there is so that we can actually have within the press area to press sideways on the panel in order to have nice tight edge joints, which you see on the left picture. All of those boards are nice and tight to each other. In the picture on the left, we have openings, and those are for post-tension anchor rods for a shear wall. This is for the shear wall that we saw the shop drawing of earlier. We then take those billets and we put them on a CNC machine. And that CNC machine gets uploaded with the 3D model that we created earlier. And this CNC machine can do any of the millings, drillings, daps, routing, really any of the wood removal that's necessary for each particular project. You can see the picture on the right has a panel-to-panel connection, like a dado that's going along the length of the panel, as well as a notch. The picture on the left is simply panels that have been trimmed. You can see they're nice and flush, nice tight edge joints. Once the fabrication is complete, we can do additional items like assembly or sealer. The picture on the left is of a wood double T, and that's something that can be complete in the shop using 2 glulam beams with a CLT panel above, structural wood screws either perpendicular to the face of the panel or inclined. The picture shown, you can see the inclined screws that had a standoff for a concrete topping slab. The picture on the right is simply a sealer being applied. That sealer will then be back brushed and give a good architectural finish to whatever the specifications of that particular project may be. Here you can see those wood double Ts attached to a hybrid structure. All those wood double Ts were set into a precast concrete girder, and it worked out really slick. This is something that we're seeing a lot of. A lot of mass timber structures are actually hybrid structures, and this particular structure went up very quickly. Each floor plate was about 25,000 feet, and the contractor was able to utilize precast concrete columns and girders, and then wood double Ts in order to lay out that entire floor plate in about 10 days. That included the topping, concrete topping slab. So really, high rate of construction, very precise, and these buildings go up very, very fast. You can see some more pictures of panels that have been sealed here in our shop, both on the left and the right. Oftentimes we have panels that are, one coat sealer, whether that's just a waterproofing membrane or actually a stain, whatever that may be, that's currently being done. Once we have the panels that are wrapped, they're now fabricated, sealed, any assembling that may be done, we need to figure out a way to get these panels onto trucks and into buildings so we can apply lifting anchors. Oftentimes lifting anchors are as simple as just a structural wood screw or a lag. Other times they may be a yoke, which is essentially like a plate with a D-hook that can be rigged up on site. Once the panels are loaded on the truck, they're delivered to the job site. Oftentimes these projects are just-in-time delivery. What that means is that there's no staging. We are grabbing the panels directly off of the truck and placing them in the building. This can be a challenge sometimes to coordinate. Logistically speaking, if we're located in Oregon, if we have a project in Portland, we're 3 hours away. If we have a project in Denver, we're 1,000 miles away. It can be a challenge to make sure that the logistics work to ensure that you don't have a crew standing around with a crane, etc. So that's something we work very diligently on to ensure that that goes smoothly. Here's a picture of a panel being flown into place. And here's a picture of a panel being that has been rigged. These guys are doing a quick check of the sizing just to ensure that everything is correct. This was one of the first projects that we actually did with our CNC machine, and everything turned out flawlessly. It was excellent. But it's really important to see here just the simplicity of the rigging. This used yokes, which are essentially, like I said, a flat plate with 2 structural wood screws and a D-ring, 4 pick points. Oftentimes these pick points are located on the shop drawings. A couple of pretty pictures of some panels being flown into place. The one on the left was side yard. The one on the right was the MBEF building in Truckee, California. A few more. The one on the right, you can see just the simplicity in the rigging solution there. It's just straps slung. The building layout was such that they were able to do that without having any, structural wood screws above. So that was the route that they had taken on that particular project. Once the panels are flown in place, the next thing is to fasten those panels to any structure below. You can see here a carpenter essentially placing structural wood screws into the panels. He will go back through and use a a drill or a screw gun to drive those screws into the structure below and fasten these CLT panels to the structure. This is a picture of the Great Notion Brewery in Portland. 7-ply panel up above, 5-ply panels on the walls that you see on the foreground. These were all detailed, all manufactured and fabricated and delivered just in time. But you can just see the neat use of these spaces, and I think that that's really what people enjoy going inside of these wood buildings. The biophilic effects of them, they feel really great to be inside. So I know Lori talked about fire protection a little bit. As CLT burns, it provides a char layer. That char layer kind of helps slow that fire growth. Oftentimes what we're doing as of now is just adding mass to that wood so that once we, burn this wood for a couple of hours, it's still going to be structurally sound once it's done burning. So this particular panel has a Class A fire spread rating, which is the highest rating that we can achieve. And a 5-ply CLT panel with 2 inches of gypcrete, it can pass a 2-hour fire test. So these can be used anywhere that you need a 2-hour fire rating. And I think it's really important. There's a lot of instances where that's necessary, and the testing has been done to verify that we're getting that complete. Here's a picture of a ferry terminal in Mukilteo, Washington, and excellent use of CLT as that, getting as the roof diaphragm. Going into purlins, into a girder, into that concrete core. So what are some of the other applications? This is Albina Yard. This is a 16,000 square foot mixed use building, 4 stories, retail and office space. Neat little building. Here's a couple of pictures of the inside of that structure. You can see it's just really simple, it's elegant. Again, people like being inside of it, working there. Although I have a hunch that there's probably less people working there today than there was a year ago or maybe a year and a half ago. But it's there, it's beautiful. It's got a great stairwell that you can see here, utilizing CLT as the guards. Here's a picture of the last panel being flown. This structure utilized light frame wood walls with glulam beams for the main beams and glulam beam columns as well. And this was one of the first uses of a CLT as a diaphragm in the United States. Here's some pictures of the MBEF building in Truckee, California. Another hybrid building using steel for the lateral in one direction and the CLT for the lateral in the opposing direction. And you can see that it went from a steel frame to a fully framed in hybrid structure in about 2 weeks. And what's really neat about this particular structure is the crew had never even heard of CLT before the project that they were working on. So, and they were able to take, the first truck, they took it, they took about a day to unload the truck, get those panels in place. And by the end of the project, they were taking multiple truckloads a day. So it was really neat to see. Here's a picture of the final product of that. Block 76 under construction. Here's a picture of the Sonoma Academy. This is that curved beam or CLT panel that we saw that they were rigging. This is an award-winning hybrid structure as well. And we're also seeing full mass timber structures, complete CLT, such as this Candlewood Suites hotel. This one's located in Redstone Arsenal, which is a U.S. Army base near Huntsville, Alabama. I believe this one was built by Lend-Lease, and there's about 1 million board feet of lumber within that structure. Other uses are shaft walls. We're seeing a lot of stairwells, elevator shafts, and one of the main reasons is that you can build, a 40-foot tall wall and a complete shaft in essentially a day. I mean, these go up quick. If you're using concrete or CMU, we're talking weeks rather than days. So something that's really kind of a unique use for CLT. Here's some shear wall tops at Oregon State University. And then we have kind of some more novel uses, like I had mentioned before, stair guardrails, really neat, precise, really beautiful parts of the structure here as well. Just about complete. This is my second to last slide. I always like to show this. Basically, this is from Woodworks, the Wood Products Council, and it shows where are we seeing mass timber structures in America. And you can see there's a lot on the West Coast, but we're seeing a lot more on the East Coast as well, in the Midwest. So this is something that's really taking on not only in the Pacific Northwest, but throughout the entire country. So I think it's really important to see that. And with the code changes that Lori had mentioned, we're seeing a lot more, opportunity for tall wood as well. And these are just some of the few tall wood buildings that have been built around the world, and there's becoming more and more every month. So I'm excited to see where this will be, this particular slide, in the next couple of years, because I think we'll have some great American buildings to be able to put on here as well. With that, I think I'm complete and get to pass it over to Iain.
Thanks, Levi. That was great. And we are going to pass it over to Iain here.
Thanks, everybody. That was a great presentation, Levi. I always learn something from, when I hear you guys present. My name is Iain MacDonald with the TallWood Design Institute. We're a collaboration between two universities, the College of, and three colleges within those universities. So Oregon State University is our home base. The College of Forestry and the College of Engineering are our partners there. And then down at the University of Oregon, which is about an hour down the I-5, the College of Design, mostly the Department of Architecture, is our third partner. So the aim of our collaboration, which has been around about 5 or 6 years, is to try to grow the manufacturing base for structural wood products and systems in the US. And we do that by trying to eliminate barriers and stimulate demand for structural wood products and building systems. It's important to note we're not really just interested in tall wood buildings. We see the sweet spot for mass timber actually is kind of between 5 and 12 stories, above where light frame is competitive and below where concrete is really hard to beat. So tall wood is just a name to try and grab your interest. And we do our work in 3 ways. We do a lot of applied research, which is the focus of my talk today. And then we sort of related to that is product testing and development for specific buildings or specific products. And then we kind of try to disseminate that through education, workforce training, and outreach. When we look at the barriers to mass timber adoption, this is kind of a pretty good summary. In order to tackle those, some of them can be tackled through applied research, and we're hard at work doing that, as well as others around the country, like the American Wood Council and the Forest Products Lab in Madison, Wisconsin, and numerous universities. The work that we do on research eventually kind of filters its way into, the data is used to kind of evolve and refine building codes, and we've recently seen that, of course, with the TallWood code provisions coming into the IBC. And then these barriers are kind of the ones that we tackle more through research and education and outreach. So tackling that, essential, that familiarity gap among players all along the supply chain, and as well, trying to address some workforce skills issues in the manufacturing sector. So when we look at applied research, this is some of the kind of a synopsis of the work that we have going on at TallWood. We have around, I think, 50 projects over the last 5 years on mass timber, and about 35 professors at the 2 universities actively engaged in working together on these things. A huge one is structural, and Lori already kind of talked about this a bit. We kind of have a scale. We go from the micro scale, the fastener connector scale, which is of course really, really important, through assembly of the building assemblies all the way to full systems. And the connectors are as important, I think, as the wood elements themselves in terms of how the building performs. So there's a lot of work going on in that respect. When we this project is just an example of some of the stuff that's going on, where this was a seismic retrofit system that was conceived and designed for unreinforced masonry structures, with the thought that maybe you could design something out of mass timber that would be able to be rapidly deployed, and assembled inside the URMs without the need for, without causing excess disruption to people in the building, and cost effective, and something that obviously could be, done at reasonable cost. That work is still ongoing, but the results are quite promising. So, diaphragms are a very important topic, and I think, we're looking at the interaction between different product species, different connectors, screws, nails, proprietary systems, the interaction between concrete slabs and the wood itself, the strength and stiffness of all those materials. So that's kind of a never-ending body of work that is quite active at OSU. Another application of our seismic work is this post-tensioned rocking shear wall that Levi mentioned earlier, and these are D.R. Johnson panels, of course, on our P.D. Hall building. So these are essentially, there are these elements at the edges, these U-shaped flexural plates that kind of act like a seismic fuse. So in the event of an earthquake, if you're not familiar with these, basically these walls are tensioned to the ground with these steel post-tensioning cables that run all the way through the panel through these channels that you see here. That are very tricky to fabricate. So good on you guys at D.R. Johnson. But essentially, in an earthquake, there's a point here where the panels are attached, but they can sort of rock on their edges, on their corners, but be pulled back to the central point after the seismic event. And these connectors at the side are intended to kind of flex and deform, and will have to be replaced. But the idea being, these are fairly inexpensive items to replace compared to the building itself being unoccupiable after the seismic event. So it's kind of a move from just looking at sheer life safety to looking at the viability of the building post-earthquake as well. We have done some work with other universities. This is a 2017 test involving about 6 or 7 different institutions down at UC San Diego Shake Table, where we tested a 2-story structure with very promising results. We tested a variety of connectors, including, there's also the rocking wall system in there as well, by the way. The results were really good, and we're kind of building on that now. We have a spanking brand new lab at Oregon State that we're going to be putting to work to do a 3-story test later this summer. And basically, this is kind of iterative work where we learn from one test and we apply it to a larger or a different kind of test. And in the next test, we're going to be looking at 3 different what we call spine systems, so lateral systems using different solutions, and attaching them to this 3-story building that we're going to be assembling on our strong floor at OSU. And this is all part of kind of a, as I say, a very comprehensive effort where we've gone from this 2-story test in 2017, doing this 3-story test this year, and then later this year there's a 10-story test that will be on the Shake Table at UC San Diego. Again, a multi-institutional collaboration there. And then we're also looking at taking the top of that building afterwards and testing 6 stories. And why would we do that, you ask, when we've already tested 10 stories? Well, 6 stories is maybe more likely to be in the market that a lot more wood would go into. There's a lot more call for 6-story buildings and 10-story buildings. And the kinds of behavior of the building, the way you design in response to that does vary. And so we learn things every time we try a different combination of these things. Of course, they are expensive and take a lot of time to plan. So just a shot there of our lab, or at least half of our lab. You can see this looks like a glorified storage area right now, but we'll be assembling this 3-story building nestling against this L-shaped reaction wall here. I'll look at some of the other things on the research world. Using our new PV Hall building as a living laboratory, so we've equipped it with about 130 different sensors. We're using it to really study the post-occupancy performance, I guess, of these buildings. We don't have a lot of data out there, even though you know, these buildings have been around for a few years, but one of our professors, Maria Paula Riggio, is active in real-time monitoring of these structures. Another important area is looking at the impacts or the interrelation between moisture and strength of wood connections. And we have a large project ongoing, which is looking at different kinds of moisture exposures and drying cycles on the mechanical performance of mass timber connectors, looking at various species and different kinds of connectors. We don't have results yet, but we're already learning a great deal from this work. You know, Lori and Levi both talked about fire testing. I won't dwell on this because you guys know all about charring and everything. This is just a couple of the different projects that OSU has led on fire performance. This one's looking at penetrations through the panels themselves, and you know, the performance of fire stopping materials, intumescent coatings and stuff like that, that would, you know, prevent fire spread from going through the penetrations. This is Erica Fisher, one of our structural engineering professors, who's looking at timber concrete composites, and this particular test was with CLT and also NLT. And you can see that's the penetrations test before we actually exposed it to the furnace. Another important area is acoustic performance. You know, the challenge here really is that there's enormous body of material, of data and literature on the acoustic performance of assemblies that were, you know, built around steel and concrete, but very little for wood. And we're learning about this all the time. And there's a dearth of data for designers, and that sometimes scares them off, and they, you know, are leery of trying mass timber. So we've done some different sets of tests looking at different kinds of layups with things like CLT with different kind of Acoustimat solutions on top, and concrete toppings and all of that kind of stuff. And we have that data is available on our website. Durability, again, we're well equipped at OSU to look at moisture and durability and things like the effects of moisture on the job site during construction. CLT is intended to be a dry application, but of course it gets wet when it rains, especially in the Pacific Northwest, and we're studying the effects of that. And so far, you know, generally, if you have a good dry out schedule to your building and you take time to carefully bring down the moisture content, get rid of the water, there are no reasons why there should be any long-term problems. And then a really important area of work is underutilized species and small diameter wood and the like. And, you know, the U.S. Forest Service, you know, spends half of its, I think it's like $650 billion or something, spend half of their annual budget fighting fires. So there's an enormous drive to try to look at ways to take, to restore those forests by, you know, we have overstocked forests in the West. It's resulting in these catastrophic wildfires. So we need to be able to take that fiber out of the forest, allow the remaining, the older trees to grow and thrive, and meanwhile have, you know, find commercial uses for this low diameter, this small diameter wood, or perhaps there are lesser utilized species like ponderosa pine. So we have quite a bit of work ongoing on that, looking at the viability of using kind of lesser utilized species for mass timber. And basically what we're finding is, from a technical point of view, you know, the design values may be slightly lower for those species because they have less strength and stiffness, but it's probably going to be adequate for certain applications. What the challenge is actually figuring out the business case. How do you bring the material from the forest to the processing facilities, to the mass timber facilities, and still manage to for it to be commercially viable? So that's the thing that still, I think, needs a lot of work. We have a really excellent energy studies and buildings lab at University of Oregon that has been doing really exemplary building science work for 30 or 40 years. And you know, some of the projects I just wanted to quickly touch on that they're doing. One is looking at how can mass timber buildings perform equally to concrete buildings in terms of the thermal mass of the concrete helping to even out the temperature flows in the building, you know, basically absorbing heat during the day and releasing it gently at night. And you know, the current work has found that, you know, a metal frame building with concrete slab floors is outperformed by a mass timber building, but the mass timber building is still outperformed by a concrete building in terms of that night flush and thermal mass effect. So we need to look to design innovative design of the building itself to try to compensate for that with mass timber buildings. And then kind of a quirky project. This one looked at occupants' perception of comfort in different kinds of buildings. So we put them in these test subjects in a chamber and subjected them to different kinds of temperature variations and also different kinds of airflow, cold and warm. And we asked them to check, tell us when they felt cold or warm or comfortable. And what was interesting was that in the mass timber building, or this simulated mass timber building that we kind of created, occupants were willing to experience a wider range of temperature variations, either cold or warm, without feeling uncomfortable. So that has implications for the overall, heating and cooling requirements of these kinds of buildings versus something that's done in concrete, for example. So an interesting area of work that's been getting a lot of attention over the last year on indoor air quality and microbiomes. And so microbiomes are kind of these communities of, viral communities and bacterial communities that exist everywhere in the world in our own bodies, and we carry them around with us. And there's good anecdotal evidence to suggest that there are positive microbiomes that are kind of created with wood in the indoor environment, and we're looking at that with a lot of interest right now, especially in the last year. I wanted to flag that TDI works with manufacturers, and we both the Oregon manufacturers of mass timber, D.R. Johnson, and this is Freder's Lumber with their mass plywood panel product, and we've had a really great relationship back and forth, and we're always grateful for the support of the manufacturers in helping to further our own research. And then my last couple of slides here, I shouldn't close without mentioning costs of mass timber buildings versus conventional buildings. It's a big area of interest, and you probably know that the conventional wisdom is that with mass timber, as Levi said, you have this longer pre-development period where you have to do things like 3D modeling, digital twins, and all of that. But then the construction period itself can be a lot shorter, and this is kind of the expensive part, because this is where you have to rent cranes and scaffolding and carry a lot of insurance and all of that stuff. So if you can shorten this, ultimately, overall, often these projects are outperforming concrete in terms of costs, even though the material costs themselves are higher. So we have some work looking at that. And then this one is a huge bottomless pit, this area about carbon life cycle analysis, impacts of forest management on how supposedly green these products are. We know that mass timber has incredible sustainability benefits in terms of sequestering carbon through the life of the building, and having a much lower embodied energy, so that the energy required to produce mass timber compared to concrete and steel is just very much lower. But we're still learning about exactly how can we tweak that to get the optimal environmental benefits from these building systems. So I'll end there, and hopefully I didn't run over time too badly. Thank you.
Thank you, Iain. That was great. And I will go ahead and take the screen back. So I appreciate both of you. That was excellent. And I know that I have learned from both of you in this process of preparing this program. So a lot of great information. Let me get my screen up. So we had a lot of questions come in. We'll do our best to address all of them. But the first question that I wanted to address, well, there was kind of a series of questions related to some of the different resources out there that are available for mass timber for CLT. Obviously, anytime you're undertaking a mass timber project, you're going to need to coordinate. So, any individual questions on specifics should be discussed with your mass timber supplier. But for general information, AWC, we have on our website, on our homepage here, we have our Tall Mass Timber site that provides some information on some of our fire testing. It provides the 2021 IBC code changes that you can see as I scroll down here. It's got a list of some of the other e-courses, recorded webinars that we have done on CLT and mass timber, as well as some additional resources. So that's a great place to start. Woodworks is our partner organization. They have a lot of great information on their website as well. So their website is just woodworks.org. If you navigate on their site, they've got a whole section of their page related to CLT, and I won't be able to name all of the resources they have because again they have a lot just like we do, but they have this really nice index of mass timber connections. So I did see some folks that had some kind of specific questions on some of these connections. So check out this guide that Woodworks has that might answer some of your questions. And then finally, the other kind of industry related resource I like to share with folks is ThinkWood. They're another organization that we partner with very closely. Their website is thinkwood.com. You can see they have resources for mass timber on their website. They have this new mass timber design manual, as well as some other information on other mass timber products besides CLT. They've got nail laminated timber, dowel laminated timber, glue lams, and other mass timber elements. So those are just a sampling of the resources that are available from the wood industry. And then there's one other thing I wanted to share with folks. We had a lot of people asking questions and saying, and very astutely noticing that both of my co-panelists today were from Oregon or from the West Coast, and asking, if there was any CLT happening on the East Coast. And there is. I am the East Coast girl. I live in Richmond, Virginia. And I just wanted to share with you, this is a building that's going up in Charlottesville, Virginia, which is in the central part of the state. That is going to be 6 stories of CLT on top of 3 stories of concrete when it's done. It's the Apex Clean Energy building. So that is a building that's going up on the East Coast right now. So I would be remiss if I didn't give a little love to the East Coast. But all right, jumping into some of the more specific questions that that my co-presenters might have some input on. First one is CLT shear walls, and both of you I know touched on this. Iain, you mentioned some of the research that's been going on CLT shear walls, but and I think Levi, you and I had talked a little bit about it. There are a lot of questions about designing shear walls for CLT. The first thing I'll say about it is that in the 2021 special design provisions for wind and seismic that AWC has just released, there are provisions in there that allow for the design of CLT shear walls. It does ask you, tell you, refer you to the manufacturer. So Levi, would you like to talk about some of the design provisions, how your organization, DR Johnson, typically handles in-plane shear and that kind of loading?
Yeah, absolutely. So we have done testing on all of our CLT panels, 3-ply, 5-ply, 7-ply, several of the grades, really to develop an in-plane shear strength. So we have those values available, and we can get those to anybody who requests them. I think it's in our product report, which is called a PRL 320, and that's available either by contacting us or through APA, the Engineered Wood Association's webpage. Also, a lot of times with the CLT shear walls, CLT is extremely stiff, and it's ultimately the strength of the connections that kind of determine the strength of that shear wall. So I know that that's something as well that we see a lot through either proprietary connections or just straight up design connections. And I think that you know, Iain may be able to touch a little bit more on some of the research that's been done through rocking shear walls and others. But as far as legitimate in-plane shear wall values, we have those. A lot of the other manufacturers also have them, and they're available out there. So
yeah, I don't really have too much to add. I mean, a lot of the research is sort of looking at the ductility you can gain from the connections, you know, to kind of address that stiffness, and you know. But if anyone is interested in learning more about the work that's going on at TDI or elsewhere on seismic, you know, just shoot me an email. I'll be happy to track that down for you.
Great. Next questions that came in were related to fire retardant treatment or preservative treatment, whether or not these panels that were being tested had any sort of treatment applied. I will say, as far as the testing has gone, these panels were all constructed with untreated lumber, so there was no preservative treatment chemicals or fire retardant treatment chemicals applied. I am pretty confident in saying that I don't think any CLT manufacturers are manufacturing any sort of treated panels, because there can be some issues with adhesives and treatment chemicals not playing nice with each other. So the typical approach for the fire testing, you know, as I mentioned, we had an untreated panel. There either will be allowed exposed timber, in which case we would design that for a fire exposure per the IBC requirements, 1 hour, 2 hour, whatever. For insects, termites, things like that, that is something that is can be done in a number of different ways. But the thing that I like to point out most when people start asking about things like especially termites is that this is a new product, but it's not a new material. So the ways that we have dealt with termites in the past, a lot of them would be ways we would deal with termites in mass timber buildings. So one way that you know, we're seeing folks avoid the problem of insects is through the use of a concrete podium. And I showed the building that's going up here in Virginia. They have a concrete podium. Many of these structures, as Levi pointed out, are hybrid. So simply having a floor of concrete will usually bring your CLT far enough away from the soil that it doesn't become an issue. But again, there's really not any sort of treatments that are being applied to any of these materials. I don't know if either of you wanted to comment on that.
Yeah, I'll just quickly say we have a little study going on right now looking at, we've pressed up some CLT using preservative treated wood, two different kinds of preservatives. I couldn't tell you what they are, but you know, that's looking at termite resistance for Hawaii specifically with you know, University of Hawaii partners. So we hope to have some data on that quite soon, but I'm not aware of any manufacturer that's been using you know, preservative treated wood for the reasons you mentioned about interactions with adhesives, you know, the effects being unknown. This is something we're trying to get a bit of a handle on.
And we have actually utilized some products that are fire retardant treated, but these are spray applied after, you know, the adhesives have been you know, bonded. So we have a full CLT panel, and you know, you apply 2 coats of a product. I think the product we used was a Sanson product, and that provides a little bit of extra fire retardant capability. So there are some products out there, but there's none that are being applied really, you know, on the individual lamella prior to bonding, for sure.
Great, awesome. Questions on size limits on panels. This probably would be a better one for Levi to take first.
Yeah, so
How big can we go?
Yeah, oftentimes we have, you know, at our facility, our limits are 10 foot wide, 42 feet long. We can press panels that are 3 3/8 inch 3-ply panels, all the way up to 9 5/8 inch 7-ply panels. There's other manufacturers out there that can press up to 12-foot wide panels, 60-foot long. Some manufacturers can press 4-foot wide panels, 60-foot long. You know, there are a few manufacturers out there that can press 9-ply panels upwards of 12 inches. So there's quite a few different sizes available out there, and I think it's really important just to note that you know, kind of see what manufacturers are in your area that may be capable of producing the project that you're going to be working on, and kind of design within those bounds. And
all right, let's see. We've had a few questions come in on fire and fire codes. I won't say too much on those because we have done a lot of webinars that deal with fire and mass timber panels, but I will say that there are provisions that do apply to mass timber structures, especially in the 2021 IBC. There are some special provisions that will apply related to you know, fire extinguishers, to fire department connections and supplies during construction. So do be aware there are some provisions that might be unique compared to other types of buildings that you've worked with in the past. And I'll just refer you folks to AWC's website on that.
And we do have several e-courses. So
yes, thank you,
on our
Marcy.
website, go to education. So.
Yeah. All right. Oh, here we go. Here's a question. So this is kind of related to transportation as well as construction. So when we get our panels, you wrap them up at the factory. They have their packaging. And then when we get them on site and they're craned into place, what about the moisture management of the panels? You can see we've got my picture of the screen up here. So we have all this exposed CLT. What do we do if it gets rained on? How much rain can it take? Are these things that the manufacturer or the developers have considered? So I'll let Levi take this one again, and then let Iain chime in.
Yeah, for sure. So, you know, we're in the Pacific Northwest. It rains a lot up here, and this is something that we've spent a lot of time on as far as coming up with good moisture management plans while on site. And you know, it's as Lori mentioned, CLT really is intended to be an interior use product as of now. And so it is important to have that moisture management plan. Sometimes it can be something simple as far as, you know, if a rain event occurs, having a you know, a laborer available to be able to push water off the top of the CLT panels. But a lot of it comes down as well as, you know, whenever the panels are being installed, if there's a panel-to-panel connection, maybe with a plywood spline between the two panels, there are ways to, you know, prevent water from running down that connection, whether that's a caulking, an adhesive tape, or you know, additional moisture management sealers, just to prevent water from, you know, to allow it to bead and not absorb into the CLT. What we found though as well is it really doesn't matter too much if the wood gets wet. What really matters, however, is how that wood is dried out. And you know, we're seeing plans where once a building is kind of closed up, applying heat in a very controlled, slow manner, along with you know, humidifiers to keep that relative humidity at a certain percentage, and draw down that relative humidity as the temperature is risen over the period of, you know, maybe a week or two or longer. This is one thing that I feel needs a little bit additional work, and I think Iain can maybe talk on that a little bit as well, as far as, you know, trying to standardize these dry out plans so that every contractor that comes up with a project isn't having to reinvent the wheel every single time. Hopefully that answered the question.
Yeah, that was great. Thank you. All right, Iain, this one's for you. I know you had talked about some of the other species that you all have been doing some research on. What other species are we looking into? Are we limited to softwoods only? Has there been any thought of using any hardwoods or maybe some other less desirable species, traditionally, quote, less desirable species, perhaps?
Yeah, it's a great question. I think in Europe there are manufacturers that are using hardwood to some extent, but it's very niche. I mean, a lot depends on what species you have locally. For example, in Oregon, in the eastern Oregon, ponderosa pine and juniper are kind of, well, ponderosa pine is sort of a lesser utilized species, and juniper is generally thought to be a bit of a nuisance, sort of invasive. And I don't think there's much. I don't think the properties of juniper lend themselves very well to something like CLT, but ponderosa pine definitely does. And we're also we're doing some testing to PRG 320 standard, not for certification, but just to try and get an indication of properties with white fir from Northern California. And that's being done for the California Cal Fire and the burn of forestry there. So we fully expect that white fir will be absolutely adequate. It's just a question of how much do the design values vary. Doug fir is kind of just this great material that grows like a weed in Oregon, but it's just a great commercial species, and it's strong and stiff, and it's hard to beat. But I think there will be opportunities for certain places in certain buildings. You don't need the same strength and stiffness, and so something like ponderosa pine might be quite usable. One of the things that our research team was looking at is, could it be used for kind of more lower rise modular housing, for example, for affordable housing? And there's a whole other set of challenges there around the affordability part, and light frame being very hard to beat. But I think we're going to find, as we sort of delve into the species mix more around the country and around the world, we'll find that there are species that are really good for certain things and not others. And then it's just going to become a more nuanced conversation when it comes to what you use to design your building.
Excellent. We had a question come in on R values of CLT panels. I can speak to this one a little bit, and either of you would be free to chime in. So the R value for wood is 1.5 per inch, or sorry, 1.25 per inch, I believe. So it will depend on the thickness of the panel, but as those of us that have studied, thermal barriers and thermal efficiency know that, it's going to come down to the insulation around the openings. But with a CLT exterior wall, you're not going to have thermal bridging like that would occur with a stud wall, for example. So you do minimize effects from that. So in terms of thermal performance of CLT walls, the thermal performance is very good. All right, let's see, lots of other questions. Thank you everybody for keeping these questions coming in. So I think we addressed predominant species, as Levi and Iain mentioned. I think it just kind of depends on where the panels are being manufactured. There are some plants that are going up under construction or in the southeastern United States that are going to be producing southern pine panels. There are some manufacturers up in Canada that are using different species of pine, I believe. So there are more manufacturers coming online. Let's see. Oh, here's a good question. Levi, you might have some experience with this. If we have a panel that gets damaged, either during transportation or during installation, are there standard details available for repair?
So as far as panel damage, oftentimes panel damage that would occur is generally more aesthetics than structural. If we have if a panel, say, was to get dropped, we would really want to take a look at that panel prior to installing that into a building. It's likely that maybe we don't actually install that particular panel, and we get you a new one as quickly as we can. If it's a minor damage, say, maybe they're installing these panels with a forklift instead of a crane, and a forklift kind of damages maybe a small corner, or something along those lines. I don't know if there's really standard details available, but there are some allowances for doing minor repairs, such as like a Dutchman or an inlay or something along those lines. Other damage that we do see during construction is, even in the picture that's shown here, we have cold formed steel framing going in between the mass timber floors. And say the framers are cutting that CFS steel on the CLT panels, and there's a stream of sparks that are, you know, flying up against maybe not the CLT, but the glue lam or something along those lines. Well, those sparks, you know, have little ferrous metal that shavings that get impregnated into the wood, and if there's a little bit of moisture in the air, a lot of times that'll turn black, and then you have maybe not a structural concern at all, but you have an architectural or aesthetic, you know, damage that needs repaired. And oftentimes that could be cleaned up with a you know, an industrial cleaner, or simply sanding. And I think that does occur sometimes, where, you know, either beams or panels or columns, they just need sanded. We try to do as best as possible to prevent that from occurring and prevent trade damage from occurring. But yeah, I think as far as, you know, small Dutchman or sanding or cleaning, those are all things that can occur and you know, help fix any damage that may occur.
All right, awesome. Okay. Iain, we've had a couple of questions about that rocking shear wall, the post-tensioned rocking shear wall that you had on your building, I think it was on campus. Can you speak to that anymore? Of any of the? Let me see. I think I've got the picture here, right?
Yeah, sure.
Yeah, here we go.
So this is a system that was developed in New Zealand after the Christchurch earthquake, where they had something like 1,200 buildings in the center of, the city were condemned, you know, and there was relatively little, loss of life during that earthquake, but the city almost went bankrupt from all of the, the building damage. And so they developed, researchers at, I think it was University of Canterbury, developed a system for use with LVL, this rocking wall system, and it's borrowed from post-tension concrete systems, of course. FP Innovations, who are kind of the predominant wood research institute in Canada, then kind of took this on and tested it with CLT. But this is the first installation, I believe, in the US. It's a more expensive way of managing seismic, of course, but we used it on our College of Forestry building because it was intended to be a showcase of what could be achieved. Having said that, you do have these positive benefits. If there is, we know there is going to be the big Cascadia quake eventually. And when it does come along, hopefully this building will be in a better position at the end of the day, in that, it will be, will preserve the structural integrity of the building itself. There is various data that's being generated from different research projects, and that's available on our website. And if you don't see what you find there, just shoot us a line and we can provide any further updates.
Excellent. We've had a couple of folks asking questions about, are there any instances where CLT has been used in exterior applications? And I want to say one of you showed a picture of, I think maybe it was an observatory or something, where some of the mass timber on the underside of the roof might have been exposed to the elements. But perhaps while I'm finding, I think this was it. I think this might have been Levi's portion. But Levi, can you talk about how we can see, maybe the underside of the roof here it doesn't have any sort of membrane protection or anything like that?
Right.
Is that, sorry, go ahead. Yeah.
Yeah, so generally, you know, these are not fully exposed elements. So it's maybe a soffit or a canopy similar to what we see here. And really that moisture content should be less than, you know, a fully exposed element. And they may have needed some special approvals from the city to be able to put in a project like that. Or some you know, professional judgment as well. But generally, you know, I know there is testing ongoing for using CLT in cases like bridge decks and others. But generally, as of now, the PRG 320 does limit you know, CLT for interior use. And although we have seen a fair amount of, you know, soffits and overhanging eaves, cantilevers, etc., so long as they're generally protected from, you know, standing water.
Right. And again, you know, these are things, you know, we've seen in other instances, other buildings may have had, for example, exposed glulam beams in a soffit application like this. So just, you know, stating again, and the things that we're using, the techniques we're using to manage moisture, things like that, we're not really reinventing the wheel. You know, this is a new product, but not a new material. We've been working with wood, you know, as a society for thousands of years. So, you know, there's really a lot of tools out there that we're simply adapting to the new product. Oh, actually, here's a good little question. CLT versus glulam, what are the differences? And that's actually a great question. Last month, we did a panel discussion on glulam where we talked about that a little bit. But the primary difference is that glulam members are carrying loads in one direction. So we see some, I think we have a few glulam columns probably in this illustration, for example. So glulam members will be beams, they'll be columns. They're typically not going to be carrying the load in two directions. They're uniaxial members. So they have one major axis that carries the strength in that direction. For CLT, these are panel products, so they are carrying the load in two directions, and that allows us to develop what's called a major and a minor axis. So it does eliminate things like needs for like interior beams or interior supports. In some cases, you can get rid of those and simply have a self-supporting panel like what we're seeing in this illustration here. We have the columns that are supporting it, but you notice we don't have any intermediate joists or girders or anything like that. The panel just kind of floats. All right, how are we doing on time? We got some time for a few more questions here. Thank you everybody again for all your submissions. These are still rolling in fast and furious. Let's see. Do we have guidance on fire protection during construction? I'm going to refer you to our e-course on that topic. My colleague Ray O'Brockie has given a couple of talks on that, so that's another one. Check out our website, awc.org/education, because Ray has given a couple of hours on that, and anything he has said in those longer sessions will be better than the 30-second answer I might be able to give you here. Let's see. Oh, here's one for you gentlemen. What are typical span lengths for CLT? I know we talked about panel sizes, but does that in any way correlate to span? Are the panels always self-supporting? Do we need glulam beams supporting them sometimes? What's being pumped out of the mill at DR Johnson, Levi?
Yeah, so oftentimes CLT, bare CLT is actually vibration controlled. So, you know, the perception of movement as somebody was to walk across the floor, at least in a, you know, a floor application. So for a V1 grade 3 ply, which is kind of a low grade CLT panel, but very common, you know, you're looking at about a little over 12 feet for a vibration controlled span length. And then for, you know, on the other end of that spectrum, I guess within that same grade, you know, if you're 3-ply, you're a little over 12 feet. If you're a 5-ply, you're about 17 feet. And then a 7-ply, you know, you're just over 21 feet. And if you were to go up to a greater grade, it may be, you know, for a 3-ply, you might be 13 or 14 feet, 18.5 feet for a 5-ply, and, you know, about 23 feet for a 7-ply. Those are simple spans. If you've got multiple spans, those will increase. And then if you go with the timber concrete composite system as well, you could likely increase those spans also. So there's lots of different ways to do that, but I mean, generally they are relatively short spans in most instances.
Right. Okay. Iain, this one I think would be good for you. What kind of, let me see if I can get a picture of your building. What kind of exterior does your CLT building on campus have in terms of the exterior wall finishes, insulation, things of that nature? Is it exposed CLT on the outside? I'm assuming it's not. But can you talk a little bit more about kind of what does the outside of the building look like?
Yeah, sure. It's actually quite unusual. So it's red alder, which is you know, sourced in Oregon. One of the goals of that building was to really try to make it a showcase of Oregon wood products, and, you know, being the center of lumber production in US, that's not too difficult. But the cladding is not CLT; it's an exterior prefabricated alder cladding, which was actually acetylated. So it's essentially it's treated in a way. Essentially, you're like pickling the wood, and this is a process that's done by a company that the product name is Akoya. It's a proprietary process. So, you know, what that allows is it gives it a 50-year service life, and it's, you know, more, what I understand is it's more environmentally friendly than, you know, slapping on, you know, some kind of stain or, you know, some kind of clear coat or something like that. And, you know, obviously with the 50-year service life, you know, a big consideration was you didn't want to have to be redoing the coating every 5 years or whatever it might have been. So the coating does naturally kind of discolor or fade, you know, so much like if you have, you know, cedar shakes or shingles, where, you know, it goes from kind of a yellowy orange color to kind of a silvery. So that's, the building's kind of in the process of doing that, and actually makes it quite interesting in my opinion. But yeah, it's quite a unique treatment. You don't see that on too many mass timber buildings. Often they're, you know, there's some metal cladding or something completely different on the outside.
Yeah, that is pretty unique. I was just going to add, yeah, I should have added that is certainly not the, as you said, the standard exterior application. We'll typically see, you know, some type of exterior insulation on the outside of the wall. In the 2021 IBC, there is a requirement that there is a layer of 5/8 type X on the exterior side of the CLT. Obviously, that would be, you know, inside your moisture barrier, but that's just for additional exterior fire protection. So the exterior of these buildings can range. I've seen facades that are brick. I've seen, you know, some architectural facades made out of wood, like what Iain described, that have been treated for exterior exposure. So, you know, what the question of what does the outside of a CLT building look like is, you know, the answer could be the same as what does the outside of any building look like. It can look like a lot of different things. So the point with CLT, again, it's not meant necessarily to be different. It's meant to fit into the existing building code, and you know, allow us to build wood buildings in a different way with this new product. So all that I'm going to address are kind of related and they are related to CLT for use for resisting lateral forces. So I know in our recorded session there, we talked a little bit about the in-plane shear values that a lot of manufacturers were using, that had been developed through testing. But up until now, we really have not had a standardized way to detail CLT lateral force resisting systems. So there wasn't really anything in the standard that dealt with CLT diaphragms or CLT shear walls. We do have the 2021 version of our special design provisions for wind and seismic. That is, it is out. It's not available in hard copy yet because we're still finalizing the commentary, but that should be available within the next couple of months. But you can see the standard on our website, awc.org. But we have had many questions, not just today, but about CLT shear walls, CLT diaphragms. So I have a little bit of language here detailing the provisions, or kind of not detailing, but just kind of outlining some of the provisions. So CLT shear walls and CLT diaphragms are going to be contained, like I said, in the 2021 version of the special design provisions for wind and seismic. For CLT shear walls, they're going to be in SPIDWIS Appendix B, and there will be alternative methods that would be outside of that as well. So that probably would cover things like that rocking shear wall that Iain and Levi talked about on the building at Oregon State's campus. But the main thing to understand, especially with CLT shear walls, is that we are really trying to uncouple the requirements for CLT shear walls from some of those that have been developed for wood structural panel shear walls. So when you design a wood structural panel shear wall, you need to follow the prescribed requirements in SPIDWIS. But the shear walls, the CLT shear walls, are associated with different seismic design coefficients compared to the CLT wood structural. CLT shear walls will have a different seismic design coefficient when compared to a wood structural panel shear wall. So there will be some differences. ASCE 722 is not finalized, but when it is finalized, the CLT shear wall provisions that are in there are going to be linked to the SPIDWIS CLT provisions. So we are in the process of getting things up to speed, getting everything plugged in together. But as I'm sure you're aware, updating standards is a time-consuming process. So not everything is going to happen with the flip of a switch. Similarly with CLT diaphragms, there's different provisions for CLT diaphragms that, again, we don't have the same requirements, prescriptive requirements. For example, there aren't any aspect ratio limits on CLT diaphragms, and we also don't have any prescribed limits on the use of CLT diaphragms in cantilever diaphragm applications in SPIDWIS. So those would be, performance-based design initiatives rather than a prescriptive limit like we see with structural panel diaphragms, especially the cantilever diaphragms. So that's primarily what's going on with the lateral force resisting system side of things. Okay, here we've had one. Iain, this one, let me jump back to your slide that this was on. I believe this is the slide that was being referenced. This pie chart that has to deal with the carbon, and one of our attendees asked if you could just discuss this pie chart a little bit further, comparing, obviously this is comparing building energy consumption, but perhaps talking about maybe some of how this would relate to a CLT building compared to, maybe a concrete or a steel building.
Yeah, thanks for the question. This very complicated pie chart probably isn't the best one to display. During the webinar, I talked about, embodied energy versus operational energy, and this depicts operational energy. So we're looking at the different contributions to energy use and then therefore greenhouse gas emissions during the operation of the building. So a lot of the focus on carbon, a lot of the carbon research that's around mass timber is focused on the other side of things, the embodied energy. So how can we reduce the energy associated with the building products themselves? And of course, wood has a really good story to tell there. And we're really trying to drill down into that part of it and understand more about the complete life cycle and the extended life cycle, in that wood products can, in theory, well, we know that they can be reused. You can take glulam out of old buildings and you can reuse them in another structure. That's already been done. There was some old, nail laminated timber floors, glulam elements from old buildings being reused. In our PV Hall building, which I showed during my talk, we reused, I think, 100,000 pounds of glulam, and it was used to create the kind of signature staircase that was in the atrium there. So that said, we can reuse these materials, but it's an open question as to what percentage can you reuse, and what's the ultimate lifespan of those materials. I don't think we know, because these buildings have not been in operation long enough. So although we are looking in some ways at the operational energy, which is what that slide showed, we're focused maybe even more so on the embodied energy. On the operational side, one of the things I talked about was this night flush and the thermal massing, that this kind of radiator kind of effect that concrete has, where during the day it will actually accumulate heat, and then it will kind of gradually secrete that back into the building at night. So it helps to lessen the demands on the heating and cooling system of the building. That is something that wood doesn't do quite as well. So there's more thought needs to be given to how you can kind of compensate for that in a wood structure versus a structure that has that sort of high thermal massive, high mass of concrete. So hopefully that answers your question a little bit.
That was a great answer, and far better than anything I could have done. So thank you for that. Let's see, some questions on CLT and their properties in commercial structural analysis software products. I do believe that some commercial software products are incorporating CLT into their updates. I know that the Canadian Wood Council has a program called, the program is called WoodWorks. That's different than our partner organization, but they have CLT involved in their latest update on that. So the, again, as I mentioned, especially for things like in-plane shear, we don't have standardized values like we do for wood structural panel shear walls. So that can make certain design aspects a little bit more challenging, but there definitely are commercial programs out there, and they are working CLT into their programs as it becomes more readily available. Another question here came in about CLT manufacturers in the southern states or in the Southeast. As somebody who lives in the Southeast, I am aware that we have a great deal of southern yellow pine around here, and there are, as far as I know, there's going to be probably 1 to 2 manufacturers coming online this year in the Southeast. And I'm not sure as far as future plans, but there is more manufacturing coming online. There are manufacturers in the east coast of Canada that can also supply, throughout the United States and Canada. So we are seeing more manufacturers pop up. Again, it's just going to be a matter of time, I think, and we're all currently living through a pandemic, so I don't know what what the future will hold in terms of the rate of expansion or things like that. I don't have a crystal ball, unfortunately, but we do hope that as more manufacturers come online, that the availability will become easier for folks to obtain the product. Do we have guidance on screws or fasteners? So yes and no. The screws, the fasteners used for CLT buildings are typically proprietary fasteners. So you might sometimes see some standardized lag screws or something like that, but oftentimes most of these are being put together with proprietary fasteners. So the installation of those would be at the manufacturer's specifications. So the design of those connections, you can use the NDS yield equations with especially with TR12, that, if you have the yield properties, the geometry and the properties of the fastener, you can calculate the yield capacity, the lateral yield capacity of the fastener. But again, since they're proprietary, you will want to confirm everything with the manufacturer of that fastener. Is concrete topping on top of CLT common practice for vibration damping? It's not just vibration damping. I've seen it used in other instances for sound transmission. So one thing about transmitting sound is when you have a lightweight assembly, sound can be transmitted through that very readily. And we know that wood is a relatively lightweight assembly, being that it's, in the neighborhood of around 30 to 35 pounds per cubic foot. So with that, you'll sometimes see the toppings, 1.5-inch Gitcrete topping on top of the CLT floor slab, and that will help with the STC and IIC ratings of the assembly to help prevent sound transmission. So, we all know that the worst music out there is whatever our neighbor is listening to that we hear through the walls, and we definitely don't want to have that in any of our structures. So, that's something that has been implemented in CLT structures for a variety of reasons. Another question here, what determines what percentage of CLT will be exposed in a building? So this is, it depends on two things, I guess. It depends on the building type. So I talked about type 4A, type 4B, and type 4C buildings per the 2021 IBC. So it will depend on, which of those building types you're designing in. As I said, type 4A, we can't have any exposed CLT whatsoever. Everything on your finishes is going to be a non-combustible finish. Type 4B, there is a percentage. The actual percentage that is allowed escapes me presently, but it's somewhere in the neighborhood, I think, of 25 to 30% of the CLT can be exposed. And then type 4C is where we have the least restrictive amount of fire or of requirements on the veneer on the exposed CLT. So we can have all the exposed CLT we would like, with a few exceptions, in like shafts, or if there's concealed spaces, we don't allow CLT in there. But you can have all the CLT you want exposed in the structure, but it is limited in height. So there's that trade-off. The more CLT you want exposed, the shorter the building will be. All right, I think we talked about this a little bit with repairs earlier, but had a few folks ask if the building was exposed to a fire, what are your options for repair? And that's a very open-ended question because it's one of those things that would kind of depend on the severity of the fire. It would depend on, where in the building the fire took place, what portions of the building were damaged, how were they damaged. So, recovery from a fire is never a straightforward event, and it's going to kind of depend on, the structure and that particular fire. So there's not, that I'm aware of, any sort of standardized details that, you can say, oh, well, you just cut this off and plug this in and you're good to go. It's something that would need to be evaluated by, a forensic structural engineer or other qualified expert to determine how much capacity was left, what are the structural needs, and things of that nature. The question is, for fire testing, have there been any UL tests performed? So I know I showed a picture of a couple of our fire tests. There are dozens of other fire tests that have been conducted on this product, between the US and Europe. The tests that AWC has taken part in that have been standardized tests have all been tested to ASTM standards. So the one test I cited, the wall assembly, I believe that was ASTM E119. Some of the other tests that we did, for example, the test we did with the two-story structure in the ATF lab, that was not a standardized test because there wasn't really a standard for how to set a CLT building on fire. Weird, I know. But so from that, we kind of had several fire experts. We had, wood experts. We had people evaluate, what would produce the test that would give us the most meaningful data. So while that one was not a standardized test, we do feel that the performance of it was representative of what the product would do. So, sometimes you kind of have to go outside of the standards, especially when we're dealing in this case with a newer product that doesn't have a whole lot of standards in the US. So, but with that being said, I think this is a good place to wrap things up. We're about another 15 minutes of Q&A. So thank you, everybody, for tuning in and for helping make our first rebroadcast a success. If you have any questions, feel free to touch base with us at info@awc.org.